Welcome to The Explainer. Today, we're jumping into a classic kinematics problem from a legendary physics textbook, Irodov's Problems in General Physics. We're going to break down problem 1.34 step by step and really get to the heart of what's going on. All right, so here's the setup. We have a balloon that's rising straight up at a nice constant speed. Sounds simple. But, and here's the twist, there's wind pushing it sideways. And that wind isn't constant. It actually gets stronger the higher the balloon goes. So our job is to figure out two things. First, what's the actual shape of its path? And second, what's happening with its acceleration? Let's dive in. Here's our game plan for cracking this. First, we'll set the problem up. Then, we'll decode the balloon's velocity into its components. After that, we'll figure out its path by calculating the horizontal drift. Then, we'll get into the fun part, finding the total, tangential, and normal accelerations. And we'll wrap it all up by looking at the bigger problem-solving strategy. Ready? Let's go. Okay, so let's really get our heads around this. Picture yourself standing there, watching this balloon. It has this perfectly steady upward motion, lifting it off the ground. But at the exact same time, the wind is kicking in sideways. And this isn't just a gentle breeze. It's a force that gets more powerful the higher the balloon climbs. Our whole mission is to see how these two different motions, one steady, one changing, combine to create the balloon's final flight path. So before we can calculate anything, we have to do the most important first step in any physics problem: translate the words into math. That means clearly defining what we know about the balloon's motion, specifically its velocity components. And this right here is the heart of the problem. We've got two completely different behaviors happening at once. The vertical velocity, v sub y, is simple. It's just a constant, v naught. Easy. But the horizontal velocity, v sub x, that's where it gets interesting. It's not a constant number. It changes based on the height, y. This combination of a simple, constant motion in one direction and a variable motion in the other is what makes this such a great problem. Okay, let's tackle our first objective. We need to find the horizontal drift, x, as a function of the height, y. In other words, we're looking for the equation of the path itself. This will tell us the exact shape of the balloon's trajectory as it flies. So this is the main puzzle for part A. The velocities we're given are rates of change with respect to time, but the question asks for a relationship between x and y with no mention of time at all. So how can we possibly link the horizontal and vertical motion directly and get t out of the picture? Well, here's our secret weapon, the chain rule from calculus. It's the perfect tool for this exact situation. It allows us to create a bridge between the change in x and the change in y. By dividing dx by dt by dy by dt, the dt's effectively cancel out, leaving us with a beautiful, clean differential equation that relates x directly to y. It's a really elegant move. So after we do that quick integration, what do we get? We find out the balloon's path is a parabola. The sideways drift, x, is proportional to the square of the height. And that makes perfect sense, doesn't it? The higher it goes, the stronger the wind, and the more it gets pushed sideways, creating this ever-widening curve across the sky. Awesome. Part A is in the bag. Now for part B, we need to figure out the acceleration. And remember, acceleration isn't just a number, it's a vector. It's the rate of change of the velocity vector. So the first thing we've got to do is write down that complete velocity vector and then differentiate it with respect to time. Now pay close attention, because this is an absolutely critical step. Our horizontal velocity depends on height, y. But to find acceleration, we must differentiate with respect to time. So we have to get that y out of there. Luckily, we know the balloon is rising at a constant speed, so we can simply substitute y with v naught times t. And just like that, our entire velocity vector is now a function of a single variable, time. Now we're all set to differentiate. Okay, let's take that derivative. The second part, the vertical velocity, is just a constant, so its derivative is 0. No surprise there. The first part, the horizontal velocity, gives us a constant value. So, check this out. The acceleration vector is constant. The entire time, it's just pointing sideways with a fixed magnitude. Pretty surprising, right? This can feel a little strange at first. How can the acceleration be constant if the horizontal speed is always increasing? Well, think of it like this. You're in a car, you press the gas pedal down just a little bit, and then you hold it perfectly still. Your speed is going to keep increasing, but the rate at which you're speeding up is constant. That's exactly what's happening to the balloon's sideways motion.
So we know the total acceleration is this constant sideways push, but we can learn even more by breaking that acceleration down into its two distinct jobs. See, for any object moving along a curved path, acceleration is doing two things at once. It's changing the object's speed and it's changing its direction. So let's look at those two components, the tangential and the normal acceleration.
First, we have tangential acceleration. The easiest way to think of this is as the gas pedal component. It acts along the direction of motion, and its only job is to tell us how much the balloon's overall speed is changing at any given moment.
Then there's the normal acceleration. If tangential is the gas pedal, normal is the steering wheel. It's always pointed perpendicular to the velocity toward the inside of the curve. It's the part of the acceleration that's responsible for bending the path and changing the balloon's direction.
Now, after a bit of vector math, we arrive at these expressions. And look what they're telling us. As the balloon gets higher, as y increases, the tangential acceleration, the gas pedal, gets stronger. It speeds up more and more along its path. But at the same time, the normal acceleration, the steering wheel, gets weaker. So as the balloon climbs, its path actually gets straighter and straighter. And there you have it. We've solved the problem. But with a problem this good, just getting the answer isn't the whole story. The real prize is the strategy we use to get there. This problem is a perfect demonstration of a powerful, general-purpose method for analyzing complex motion. This is our playbook. You break the motion down into components. You use your calculus toolkit to connect variables in clever ways. You always make sure your vectors are functions of a single variable before you differentiate. And you never forget that acceleration has two jobs, changing speed and changing direction. This isn't just about this one problem. It's a framework you can use for so many other challenges in physics. And that's really why this matters. This approach isn't just for a balloon in the wind. It's for understanding the orbit of a satellite, the path of a charged particle in a magnetic field, or even the spin on a curveball. It's a fundamental tool for making sense of a complex world. So my question to you is, what other complex motions can be understood by breaking them down into simpler parts?